go at the rest of them at your leisure for practice, okay? If there are any you turn up with particular issues over, bring it up and I'll go through them best I can. Right, Kirchoff's voltage law. It's similar in many ways. Kirchoff's voltage law states that at any instant in time, in any closed loop, the sum of all the voltages is 0. Okay, but again, we've got a method, or I've got a method, of defining the way you develop a Kirchoff's voltage law equation. And that's, you do need, it's a little bit more error prone if you're not careful than it is for the current law. Okay, in that circuit, remember what Kirchoff's voltage law says, in any loop. So we've got a loop there, loop A, we've got a loop here. I'm going to call loop B, and the last one we've got is all the way around the outside, loop C. Yeah. So all of those loops individually will comply with Kirchoff's voltage law. Okay. So usually, if there's 3 like that, we'd only need to use 2 of them to completely solve the problem. The third one is a little bit of a check, because they must all comply. Yep. So the way we go about this is, the first thing we need to do, given the circuit like that, we need to put some, what I call Kirchoff's voltage law arrows on around that circuit. So where you've got a source, you put an arrow in the direction of current flow. So on sources, i.e. batteries, any voltage source, any EMF, arrow, put voltage arrow. In direction of current. So I've only got one source in this circuit. So that's the arrow there, pointing in the same direction as the current leaving that source. On resistors or any other load, voltage arrows against current direction. Through that resistor. Okay? So, given a circuit, you decide by convention which way you think the currents are going. And in here, we've only got one source. We'd expect the current to flow out at a positive terminal. Through there, we'd expect at this node for some of that current to go down the middle, some of it to carry on through this resistor, round through that one, all meet up again there to become the total current again at the bottom. We'd all be expecting that to happen. So I've put the various current arrows on there. Applying to this resistor, I put a voltage arrow in that direction. I'm going to call it V1. This resistor, a voltage arrow upwards, V2. This resistor, a voltage arrow in that direction, V3. And that one, V4. Yep, that's the procedure you need to do, and need to get in the habit of doing that carefully. please don't put arrows on both sides of your voltage arrows. One side only. The arrowhead should point to the most positive end of that resistor, which it will if you put it against the flow of current. Okay? Again, if you do one of these problems and you end up with a negative voltage, it's not necessarily because you've got a wrong answer. It'll be because that current arrow or the arbitrary decision made about the direction is actually wrong. And so the arrow's the wrong way. Alright? So it's a similar thing, but we can write 3 different Kirchoff's voltage law equations for this particular circuit. If we look at loop A, if we call this E1, because that's a source, we can say, what we do is that all the clockwise arrows, so I'm going to let's put the circuit on another page. So what I do here now is all clockwise arrows left hand side of equals all anti-clock arrows right hand side of the equals. Yep. So instead of talking about nodes now, we're talking about loop A. We'd say that E1 is the only clockwise arrow is equal to V1 plus V2. Can only apply it to that individual single loop for current to flow from the source round through and back to the source. Loop B, what are our clockwise arrows? B2 is equal to V3 plus V4. Yep. And then lastly, for this circuit, for loop C, we've got E1, the only clockwise arrow, I believe, and that's equal to V1 plus V3 plus V4. So that's the procedure for doing that. Carefully put your volt drop arrows on if they're not already there, with the current for sources against the current for resistances or voltage drops across resistors, and then go round each individual loop, putting the clockwise arrows on one side of the equation, the anti-clocks on the other. It wouldn't matter if you'd done them the other way round, it would make no difference. Rearrange for the unknown voltage and find it. So if we've got any loop where we've only got one unknown, we can use Kirchoff's voltage law to find that unknown. Well, any other component as a cast, we can simulate the load of a motor by saying that's a resistance, can't we? Or a heater, or a lamp. Yeah. If it's a resistance to current flow, then it's going to have a volt drop across it. A source, like a battery or a generator, is providing voltage to the circuit. So you put the arrow with the direction of current there. Okay? So it's distinguishing between what's driving the circuit and what's actually taken something from the circuit, usually represented in simple circuits by resistors. All right? And I know that and I'll probably end up saying this many times, and know this is looking very mathematical, but try and understand the underlying electrical principles. Voltage up, current up. Resistance up, current down. That's the principles of Ohm's law, and it comes into everything that we do, all the way to level 6. You can pull everything back to Ohm's law, and you can pull everything back to Kirchoff's voltage and current laws. They will always be obeyed. Yeah, that's why we're doing them up front. Go on, Jake. If you put voltage up, Ohm's law says you put voltage up, for the same load, current will go up, won't it? Voltage down, current down. If you put resistance up, keep voltage the same, the current will go down. Resistance down, current up. And I always do what happens to the current, because the current is, in any circuit, is really the thing that happens because of the voltage and the resistance. We control voltage and resistance, and where we set them to determines what the current is. We might have a power supply where we can dial in a particular current, but what we're really doing is upping the voltage and reading off what the current is. Okay? The current is as a consequence of the voltage of the circuit and the resistance of the circuit. All right? If you understand those underlying principles, the maths becomes that much easier. All right? And you will be expected to talk about some kind of principles in the exam. It's not all maths. All right? I won't go over what they are at the moment because we're a bit... As an example circuit, we've got one source, 4 resistors. How many loops? 3. Yeah, well done. We've got one there. Call it I. One there. Through those 2. Call that B. And 1 all the way round. Call that C. Yeah. Where would you start solving that problem? Loop B is an interesting one. 2 voltages. Yeah, but they are equal to each other. But loop B, V2 is the only clockwise arrow. V3 is the only anti-clockwise arrow. Yeah, well done. V2 is 20 volts. That proves the principle that 2 resistors in parallel have the same voltage across them. Yep. Now the arrows are in different directions upon this principle. So as saying, the plus 20 volts is at the top on both resistors, and the 0 volts in terms of that voltage is at the bottom. They've both got the same voltage on them. Kirchoff's voltage law proves that. Yeah. So the only unknown now is V4. Which loop are we going to use to find that? Can we lose loop A? Yep, I spotted my deliberate mistake. Current's going that way, voltage arrow that way. See how easy it is to do it wrong? Yeah, all them other ones I drew like that and put the arrow on the left hand end. Do need to be careful. So in this loop, clockwise arrows are E1, and anti-clockwise arrows is V1, V2, V3. Yeah, and we want to use it to, no, hang on, we wanted to V4. and we want to find V4. V4 is V1 minus V1 minus V2. That is 50 minus 10 minus 20 equals 20 volts. And then, so we write that on here, 20 volts, and we can use loop C, the third loop in the circuit, to check that we got everything right, because that should conform as well. We've got 50 volts there, and we've got 10, 30, 50 volts in that loop as well. So we can use the third loop available as a check to see whether we got everything else correct. Yep. There's a circuit with 3 sources, 3 batteries, connected in series, right? But 2 have arrows going clockwise. The third one has got arrow going anti-clockwise. Which way would you put the current arrow for these resistors? That way? And don't think that that circuit can't happen, because it could be 2 sources charging this source, which is a battery. Yeah. Or you put sources in parallel to get more current out of them. They'll be opposing each other around a loop. So when you want more current out of batteries, you can connect them in parallel to get more current from double the current from 2 batteries that you get from 1. Yeah. So you can end up with circuits like that. The answer is that decision is an arbitrary one in terms of you decide which way you think it's more likely to be going. Yeah. But you don't know. And until you know some other information, you can't tell. But the danger here is that current, that voltage arrow is against what our normal convention for a source would be. You just got to watch that. I've drawn that solid line that side and a dashed line that side, and by convention the solid line is the more positive side of a source, and therefore you put the arrow that way. Okay? Yeah? And it might be appropriate also to do that on your diagrams as well, plus minus, plus minus. Right? Not necessarily. You charge your battery by putting current in the opposite direction to what you take it out. Okay? If they're rechargeable, of course. If they're not, then they might well blow up. They don't like being recharged, unrechargeable batteries. Alright? So in this particular circuit, we would add voltage arrows here, call it V1 and V2 in that circuit there. And then if we knew some more information, if I told you that this was 30 and that was 20 volts, can you now solve that circuit? For voltage, can you find E1? E3, sorry, yeah. What would it be, minus 20? So you've got E1, the equation is E1 plus E2 is equal to E3 plus V1 plus V2. Yeah, everyone happy? And then we can rearrange for E3. It's E1 plus E2 minus V1 minus V2. Have I got that right? So we got 20 plus 10 minus, what did I say that was? 30 minus 20. So it's minus 20 volts. So the battery is actually not, that is actually the other way round. Okay? But you can solve the problem because in that loop, once you know all bar one, you can use Kirchoff's voltage law to solve the problem. I'm going to leave you with one problem I'd like you to have a look at between now and next week, as well as the Kirchoff's voltage law problems in your notes. Okay? I want you to have a look and think about this one. All the resistors in that circuit are of equal value. How much current flows in either direction through that middle resistor? Anybody seen a circuit like that before? If that was a bridge rectifier, what would the components be? Wouldn't have done one in the middle. What else would be different about it? That'd be diodes and not resistors. Okay, but it's a very common circuit in instrumentation. Yep. So have a look during the week. Research if you like. All right, but ultimately, Kirchoff's voltage law to prove your answer to that circuit. Yeah, all the resistors are the same. 10 volt source. How much current flows through the middle? And then up the front next week, we'll just take a look at that problem.